All right, you should be able to do all but B based on that right there. Oh, I should put Avogadro's number.
Oh, yeah.
What am I doing? That's the exponent. Okay. Does your face hurt? All right. Where's, nope, never mind. She's great. Where's, yep. Yes, sir. What?
That's like 10 to the power of
Arrow or caret, yeah.
Ah, sweet.
This could just be in a math textbook with no context, right? Like all those tweets out there, whatever, like no context, Brooklyn Nine-Nine, and you're like, that makes no sense. If the math book just gave you a variable and gave you some numbers, that's what it is, right? We don't have to have an understanding of chemistry to do this, which most kids like. We do need to know that frequency is V. So the equation we rewrite, V would be C over lambda, right? We all right with that part? Okay, I gave you C, and you should use nanometers. You don't have to, but once you do it in meters, then you got to convert it to nanometers. So why not just do it at the start? All right, so we have 3 times 10 to the 17th. We divide that by our 620, and then someone in the front row have that number still. 4.83 times 10 to the 14th. Okay, who had that?
Oh, I write it wrong.
Okay, what's the unit for that? Anyone remember? Hertz, which is s to the -1 typically. You'll see hertz in physics. You'll see per second in physics, but here you'll see s to the -1 most of the time. All right. Energy of a photon. Most of you won't use this. I don't know why, but I always go a different route. This is the shorter one, right? So now that we have frequency, we're ready to go. Energy is equal to H, which is Planck's constant, 6.63 times 10 to the -34. And you multiply that by the answer you just got right here, which is 4.83 times 10 to the 14. Yeah, this is very calculator screw upable. So I would be really like OCD on your parentheses. What I usually do, and you don't have to do this. This is Tom Davidson, who got burned with math his whole life. I will type this number in, 6.63 times 10 to the -34, and then I hit enter. And then it like pops it in down below. And it's like the same thing. But then I multiply that answer by that. I don't know if that makes sense. But that way I have everything compartmentalized. And then I can go use it again with my arrow. I can arrow up to select it and bring it down. If that didn't make sense, it's okay. Really, I tried to resurrect my grandpa here, and it just, even new batteries. I did get it to make a beep. It was like, I'm like, oh, but nothing. Really, I just had all the variables calculated, so it went pretty fast. But anyway, we have an answer right here in your calculator. What did you get? Are we okay with that? 3.208 times 10 to the -19. All right, sounds good to me. So that is the energy of a photon What's the unit for energy that we learned just a little bit ago? Joules. All right. If you didn't know that, the units of H are joule seconds, if I remember right. So the seconds on top and then the seconds to the -1 of frequency cancel out and you're left with joules. So like you could figure it out based on the units. All right, this is a photon. So energy of a mole of these, you take your answer, 3.208 times 10 to the -19, and you multiply that by Avogadro's number, 6.02 times 10 to the 23rd, and you end up with something. 125. I'll just go here. I'm okay with that. All right, and joules. Fair enough. Perfect. That's what your calculator will say. That would be the most accurate, is to write it in scientific notation. Any of them are fine. Very often, this problem asks you for the answer in kilojoules. It doesn't here, but on the AP test it will, because then it will find another question to ask you based on other things. Because we found energy here, and we just got out of chapter 5, which had energy, right? So AP likes to just throw Frankenstein problems together where all sorts of stuff, all chapters are used. So if it says joules, just 193 joules or kilojoules. All right, nothing too hard, I hope. Okay, what color is the photon? Muscle man.
Is it like yellow orangish?
It's yellow orangish. It's orange. All right. That's not that awful. On the test, your test, it comes black and white. But it says red. It says violet. So try to remember Roy G. Biv. You okay with that? It's a different number. And I'm pretty liberal with it. Like if you said orange and I thought it was yellow, I'm still going to give it to you. Don't say blue when it's supposed to be yellow. Yeah. What?
How did you figure out
The color? Well, good. I'm glad someone asked, because in the problem it says it was 620 nanometers. And if you look right here, you just come to this and right around here, 620, and you just say, all right, that's literally all you do. Oh. Yeah. Okay, can we do this problem? I know you can. Bill can. All right, everyone else that's not transferring out? Okay. Only 3 had transferred out. I don't want you to transfer out, but the way kids talk, I thought it was gonna be like 15. But okay. Yeah. Okay. Here, you may not know how to answer this question yet, but let's just talk about it. You and your friends. Talk about the relationship. Sort of yesterday, we talked about strength or energy of colors, right? And we talked about me falling off a ladder, right? So see if just you can read this and think, all right, we don't know it yet, but we're going to learn. The light was produced when an electron jumped up and it fell, and it gave out this orange color. Based on what we talked about, do you think that's a large, medium, small fall, and why? Tell your partners, not me. Yes. What did you say?
I don't know.
Then you're wrong. Go card, right? No one did. You're like, oh, he's gonna say like energy and Bohr and vomit. Okay, low energy, and then high energy. So just strictly, now this number will be different on the exam. All you have to do for this is you see, all right, well, the color was towards the red side, so it's probably a smaller fall. If it was up here, it's towards the purples, so it's a larger fall because it has purple has more energy, red less energy. I can, but there's green. And so you would say, I don't know, maybe a middle transition. It's not awful though. So give me like out of 5, 5 is I'm ready for it. 1 is I'm dropping the class. 1 to 5 on how you could do this problem in a week. All right. 3.5 is good for now. Okay, fair enough. We'll go over it again. Daniela, our perfect student that's never tardy and turns in everything on time, already did the Thanksgiving assignment and took the quiz.
I watched the video.
There you go. And the quiz is just this, right? It's just this quiz. It asks it in like steps, but it's just this quiz.
The last one I got wrong because I didn't know how to answer the.
What did you put?
I put like.
It's okay.
So what's exactly?
I can look at it. All right. I don't remember where we got yesterday, but we're gonna talk about Bohr today. Hopefully it's interesting and not boring. You guys are welcome. No? She is not a dad. Yeah. Fine. Okay. Hey, look, I feel like we had this conversation a long time ago. Large fall around blues and purple, small falls around red. Some druggie must have chose that. Totally high, huh? I'm like, give me a number. 420. Moving on. Keely felt that one. She's like, never mind. I'm not saying you're a druggie. Okay. Who doesn't? Okay, another mystery that when they were researching this stuff, what are you doing with my calculator? You found a way to play a game. Oh my laws. You're welcome to play games on your calculators, but not mine. Okay.
How did they do that?
I don't know, but don't try. Focus. Don't. Oh my laws. Okay. So remember, when they first were discovering this, they didn't know that much. They thought energy would come in, you would have a constant thing from colors, the whole rainbow would be given off and all this stuff, and it doesn't work that way. So they came along and figured out, hey, I think that energy is quantized. Everyone, if you are touching my calculator, turn it off. If you're playing on your own and you got 100% on every test, then you can do what you want, Ryan. Okay, sorry, what a loser. If I should, I'm such a waste lately. I don't know why. We just did this lab and I forgot. I took it all down. It's kind of a pain, but we'll put it back together. My TA next tries my child, so I can do whatever I want. All right, so when light is viewed through a spectroscope for electrified elements, they assumed you'd see a rainbow, but you do not. When you look and you, like a spectroscope is basically a prism that breaks light into its parts. You kind of all right with that? All right, so like who's been to the lights at Wheeler Bay? And they're like, do you want the sunglasses? And you're like, I'm not going to spend that money. Spend that money. It's 10 million times better. The glasses make everything pop. It diffuses them and you see like 3D lights. Yeah. It's just a diffraction grating. So it gives depth to all the lights. Anyway, it's that type of thing. You okay with that? So when you look at elements through one of those, you don't see what you expect to see. You only see lights in certain place, or only see colors in certain places, and the rest is white. This is called an emission spectrum. And for hydrogen, there's only 4 places where light is given off. It's around 660, 480, 410, and 460 or whatever. That's the 40, I don't know. But there's only just a few lines. And we'll look at this next week. We will do this and see these actual lines. All right. So it was weird to like, this does not seem to make sense. All right. Well, along comes Bohr. Now, don't panic over all this thing or this thing. But Niels Bohr comes up and he says, hey, I think that Planck is right. I think energy is quantized. And I think atoms with electrons in them, they're jumping up to specific places and falling back to specific places. And if they only jump to specific places and fall to specific places, then they only give off specific what's? Colors. And in fact, for hydrogen, it only has 4 colors that we see. Now, it gives off other energies, but visible light, there's only 4 combinations for hydrogen's single atom. All right. So he says electrons in an atom could only occupy certain orbits corresponding to certain energies. Yes, sir. I doubt it. Yeah. You'd see a whole lot of things. It's interesting to, like, we look at the air right now and we think, well, it's clear and it has no color. But if we could see everything, oxygen definitely absorbs and gives off certain lights, or not, I should say energies. Our eyes just aren't built to see them. So yeah, the world would look completely different. We don't really know what, but it would look different. Okay, so here's what Bohr says in a nutshell. And this is a super small nutshell, but he says, hey, we have orbits, kind of like where planets live. Planets are never between each other, right? The Earth has never traveled to Mars and back. Earth goes around in a circle the same place. You kind of with me? So an electron can live here, but nowhere else except right there, right there, and right there. Kind of like the stairs, kind of like the ladder. We use that analogy a few times for this moment. An electron can change. If it's excited, it can go up and it will fall down. And that fall from going up to falling down will give off energy. And that energy we can see is light if it's in the right energy, which produces the right wavelengths between 400 and 700. Kind of with me? There are 4 combinations for hydrogen where you have a jump and a fall that give off visible light. Do you know how I know there's only 4? Because that is the exact answer. Because when you look through a spectroscope and break it down, there's only 4 colors total when hydrogen's excited. There are only 4 combinations of where you start to where you end of an electron falling that produce light I can see. If there were more, I would see more lines. Who's sort of with me right now? Okay. Sodium, all sorts of stuff happens with sodium, but we only see a really bright yellowish orange line because that sodium with its 11 electrons, they're bouncing all over the place, but one specific combination of like going to 3, coming back to 1 or something like that is giving off that exact wavelength of light. Okay, Bohr was able to come up with this and come up with his model. Now, this right here is Bohr's model. If we were to like make these into rings, these are the places that Bohr says the atom or the electron can live. And these are the values of the energy of those rings. You don't have to do this math, so don't panic. But we have negative HCr. R is a constant as well. It's negative 2.18 times 10 to the something. I can't remember. But those are constant. And then this one is the same at 1/4, 1/9, 1/16, Any guesses on the next one? Yeah, it's 1/64th actually. Why? For fun, for math. It's definitely super fun. They're squares. All right, now, so what he's saying is an electron can be here. It can go up here, and then it can fall down here, and it would give off energy or light with energy equal to the difference between these two things. Gosh, get out of my room. All right, I love most of you.